organization committee to invite me. It's a great pleasure to stay here today. I want to show you just an overview on cholesterol photosensitized oxidation products in food systems. Cholesterol is a monomolecular monounsaturated molecule, like a monounsaturated fatty acid, and is prone to the oxidation by enzymatic activity, like it's happening in the brain, on the liver, or by photooxidation, the autooxidation, and leading to the production of cholesterol oxidation products called the COPs. But which is the difference between the autooxidation and the photosensitized oxidation? When we have a photosensitizer, such as hemoglobin and the light, we have a strict interaction, and the triplet oxygen is a stable state. It's become a singlet oxygen, more reactive. You think that we have a difference of 32,000 times more faster. So the singlet oxygen attack the double bond in B rings, and the main products is the 5-alpha hydroperoxycholesterol that is converted to 5-alpha hydroxycholesterol, and then more stable products, 7-alpha and beta hydroxycholesterol or 7-ketocholesterol. By triplet oxygen, we have also the 7-alpha hydroperoxycholesterol and the 7-beta that by dismutation form also the 7-alpha beta and the 7-ketocholesterol. Again, by bimolecular mechanism, it's possible to obtain the alpha and beta epoxycholesterol by an addiction, and when we have waters and acidity condition, it's possible to have the triol. The triol, cholesterol triol, is the main toxic of COP. So why it's important to study the COPs? The COPs are well reported, involved in many different neurodegenerative diseases, such as Alzheimer's, or diabetes, osteoporosis, and congenital failure, sclerosis. And also, they act as pro-inflammatory and pro-apoptotic, and act with cytotoxic agents, carcinogenic, and mutagenic activity. But the problem is the COPs are naturally present in the raw food. And when we use light or eating or exposition to oxygen, we increase the production of these products. In this slide, you can see the rat hepatocytes where 3 different diets were supplied. Control plus 1% of cholesterol, a control plus mixture of cholesterol and COPs. You can see we have an inflammatory process on a hepatocyte, just 1% of COPs. And again, in the aorta, you can see that infiltration of lipids in the adventitious layer of rat aorta. So you can understand that we have a big problem on safety aspect on food. This table reports some different food and the amount determined in food. You can see that when we have some technology process, such as pasteurization, we have an increase of cholesterol oxidation products. Well, today I want to show you just some data on beef sliced, pork sliced, and sardine. First of all, on beef, we used 56 animals, subdivided in 7 different diets. Control diet, extruded linseed oil and vitamin E, supplied for 180 days and 90 days at double of amount of vitamin E as in form of alpha-tocopherol acetate, because it's more stable compared to the free form. And again, CLA and the vitamin E for 2 different periods, and extruded linseed oil, CLA and the vitamin E, and extruded linseed oil, CLA without vitamin E. After slaughtering, the obtained slice, were stored for 8 hours after 15 days of weight aged at 4 degrees. This is a typical procedure used in Italy in order to obtain a good tenderness of meat. So then we store the meat slice for 8 hours at dark and expose it to light. And the results were compared with the time zero, which were immediately frozen. About the sample was extracted the lipid phase, and after isolation of unsaponifiable matter, was detected the cholesterol oxidation products by fast chromatography, gas chromatography coupled to mass spectrometry. It's possible to analyze the total COPS in less of 3 minutes, and the total sterols to compare the amount of cholesterol. The cholesterol was 98.7%, and the 1.3 was phytosterol, mainly camptosterol, beta-sitosterol, and stigmasterol and venosterol. If you can see this table, you can see that no significant effect we found related to diet and storage, but the amount of total COPS was ranged between 0.5 and 2.1 milligram per kilogram of meat. And this is the main COPS determined. But comparing the cholesterol oxidation ratio, the amount of COPS on the total of cholesterol, so the oxidized cholesterol on the total amount of cholesterol, we see that when we supply the CLA and the vitamin E, we have a reduction of oxidation of cholesterol. And the range of oxidized cholesterol ratio was between 0.1 and 0.6. So after light exposure, we have a trend of an increase of cholesterol oxidation. About pork, we used the 64 animals, subdivided in 4 groups: control group, O group where we supplied the 3% of diet by high oleic sunflower oil, and E group where just control diet plus alpha-tocopherol acetate, and OE group was control diet added by high oleic sunflower oil and tocopherol acetate. In a similar way, we stored the sample for 3 days at 8 degrees at dark, under light, and compared to immediately frozen sample, the time zero. So analyzing the diet factor, you can see that control diets reported the highest amount of COPS, but no significant effect was found considering just the storage factor. But when we studied the interaction between diet and storage, you can see that when the vitamin A was supplied on the dark condition, we obtained the lowest amount of COPS. And here you can see the cholesterol oxidation ratio, and you can see that the 7-ketocholesterol was significantly higher in the sample without the supplementation of vitamin E. Actually, the 7-ketocholesterol is used as a marker of cholesterol oxidation. And also you can see that the vitamin E, the antioxidant effect of vitamin E at dark was confirmed. Finally, on the fresh sardine, we used the fresh sardine just from a retail store, clean it, and we used the time zero immediately frozen, one part. The second part stored at dark just on the ice at 4 degrees, monitored for each hour at dark, and a similar weight at light. After 1 hour, 2 hours, and 4 hours, we sampled the sardines. So you can see that during the storage we have an increase of amount of COPS. And in particular, in this kind of sample, we found the trial. The trial we didn't find on beef or pork, but in sardine we found the trial, because remember, we have water and acidic conditions. And the range of total COPS is higher compared to value obtained in pork or meat. We reached the 3.72 ppm of muscle. It's important to note that actually we have not a limit of COPs in food, but considering COPs as unclassified compounds, according to Croes et al., we using the limit of 0.15 micrograms per person per day. So here we compare the time 0 directly with time 4 at dark and the light. You can see that the 7-beta hydroxycholesterol and the ketocholesterol significantly increased after light exposure. So this means that the light passes through the skin of the fish, because in other words, we cannot have photooxidation. So in this case, we have a rapid increase of 7-ketocholesterol and the 7-beta cholesterols. And considering the cholesterol oxidation ratio, we obtain 3 significant groups. After 2 hours of light exposure, we have a significant increase of cholesterol oxidation. And then we have the dark sample, just the similar way the 1 hour exposed to the light. And finally, low amount was found in a fresh sample. So concluding, the cholesterol photosensitized oxidation is one of the main chemical degradation that occurs in food system. The extent of degradation will depend on many factors. As you can see on fish, we have a lot of amount of polyunsaturated fatty acid. And this probably is the reason why we obtain higher amount of COPs. So what we can do? We have different strategies. We can use antioxidant. We can use low processing temperature or proper packaging, such as a lighting filter, just to isolate the different wavelengths of lights, or different light conditions. Finally, the combined use of this strategy during the commercial retail store can efficiently to reduce the cholesterol photooxidation without to have a significant difference of sensory properties. But it might be pointed out that it's needed to further research in order to define which is the actual toxicity level on food of COPs, and to have an harmonized analytical procedure to determine cholesterol oxidation in foods. So finally, I want to introduce my supervisor, professor, and my department. Thank you for your attention.
Thank you very much, Vladimiro, for your nice presentation. We have time for a couple of questions. Any questions?
What kind of methods can you use to analyze oxidation rate?
Oxidation rate is the ratio between the COPs and the total amount of cholesterol. So we determine the cholesterol by gas chromatography and the cholesterol oxidation products by fast gas chromatography coupled to mass spectrometry. So comparing the 2 different kinetics, we can calculate which is the cholesterol oxidation ratio.
Thank you. I have a question about sensory, because in your summary you mentioned that sensory was not really effective, right? How did you measure the sensory properties?
So in our department we have a group of sensory analysis. So we have a panel.
So it was a descriptive test. Okay.
Yeah.
Good. Okay. Any other
Also,
question?
we have a SP, so gas chromatography by fingerprint of volatile compounds.
Okay.
Yeah.
Okay. So thank you very much.
Okay, thank you. Vladimiro.
Thank you.